Cool. Then we would just keep moving on music search and recommendation. So again, now we are approaching sort of like toward the later part of this music production workflow. So, we talk about how you initiate an idea and, a lot of like creation tools, also music analysis. Um, but all the way until we talk about production tools, mixing, mastering, and now once you have the music sort of like treat it as a product if you like, then how do you distribute it? How do you recommend it to your listeners? How do you publish it? What are some of the constraints, what are the legal business perspectives of that? So we look at, of course, streaming now become the biggest chunk of this recorded music industry, but this is just recorded music industry. So there's also live music industry, which is another big chunk of market. But also, think about gaming industry is growing. Film industry is also large. Um, cool. So last week, not last week, on Monday, we sort of like started into looking into this. So the first thing we will look into is, music fingerprinting. So what is music fingerprinting? Basically is that we want to sort of like very quickly identify what the song that you listen to is. So, this is, most famously, Shazam. So in Siri, you can add what song is playing right now, then it will just listen to, record something. And the goal is try to identify that particular song in your huge database. So think about, Apple Music, think about, YouTube Music, Spotify. They have a huge catalog, billion of songs, millions of songs. How do you quickly identify that? And some other companies like SoundHound is also doing this. But also, most voice assistant can do this nowadays. So the idea of audio fingerprinting is that we want to get this fingerprinting model that can give you this sort of like fingerprint of an audio. And the goal is that this algorithm will be compact enough so that your fingerprint is small enough, but at the same time, it should be very efficient to find out which one is that. So the idea is that, well, you have a huge catalog of billions of songs, and then you want to get all the fingerprints. So this database could be huge, but the idea is that once you have some new audio, you want to grab that fingerprint and then you want to search it. So there are multiple constraints here, but typically our goal is to make this fingerprint as compact as possible. So as efficient that representation as possible. But at the same time, this matching algorithm has to be very efficient because you are, grabbing one and match it to millions or billions of possible entries. So this is like a common framework for audio fingerprinting. I mean, there are so many different ways to do it, but in general, the idea is just that grab some audio, you do a bunch of processing, and these processing has to be, sort of efficient and compact so that you get a very compact representation of your inputs. So, pre-processing, you can do all sort of different things, but these are very high level pre-processing. And then you can do framing overlap. So that's sort of like think about STFD, where you do slices of the frames and then you just slice through it. And then transform, you can do all sort of like STFE-ish, like DFT, discrete Fourier transform, then this becomes STFD, but you could also use other transform. But anyway, once you have the transform, you do feature extraction. You can do all sort of different extraction. If you think about just energy, then that becomes the spectrogram that we know about. And then finally, you do processing. But anyway, what you get is just something you can think about like STFT-ish outputs that capture, both the frequency and time elements of your audio. So the goal is, you have some audio and all the way you want to grab sort of something that's a representative of your audio. So I would just go through two of the iconic fingerprinting algorithm. So the first one is by this is by Philips. It's not Shazam. So this is actually 1 year earlier than the Shazam one. So if you look into this figure, you might be wondering what's going on. But the idea is that at the left you have the audio, and at the right you will get something we will see next slide. Something like this. So at the left, you have like something sort of like your audio or spectrogram like, and at the right, you will get that, sort of like QR code-ish stuff. So how does this model work? So if you take a look into this figure, that you will see these things like framing, and you have the window things. And so you have a window and you slide through your audio, and then you do Fourier transform. So these two essentially is just STFT, right? So how STFT work, as we see in the PA, is that, well, we want to do Fourier transform, but we want to localize which part of audio we are looking into. So we do this framing thing. So the first frame, the second frame, the third frame. So that's sort of like the STFT, each slice of it. And take a slice of your audio, and then you do Fourier transform. Then you get as a TFD. And then you do ABS. That's basically just taking the magnitude. So this is basically just works like extracting magnitude only spectrogram. And now if you look at the other part, that's what we will look into next. But you will see first this band division things, but looking at it, it's just like this is the filter design. So these are basically, your frequency bands, from low frequency, mid frequency, all the way to top frequency. So you want to divide it into multiple bands. But you can think about this as like the male spectrogram things. So if you look into sort of like if your spectrogram, assuming somewhere here you already did all the magnitude only spectrogram calculation, and you also do the band division thing. So, as we talk about, this is like male spectrogram as we have in PA4, where the y-axis is already being mapped to another scale, where this is log scale, and each being corresponds to human hearing range. So imagine this is what our input is like all the way until this band division. And the next chunk of these computation is basically computing what that QR code is. So how does this work? So basically, they try different things about looking into how to do that. And they figured out that energy difference is very important. So how does that work? Basically, is like grabbing this, spectrogram-like thing, and you do this convolution over these things. So 1, 1, minus 1, minus 1. And is this gonna remind you about something we've seen in SSM, right? So remember that in SSM, we are doing that diagonal things, and we want to try to see the boundary between, boundaries between sessions that also has this uh, like saddle point theater. But anyway, that's what they found really helpful. So, if you apply this to this, and you will get something like this. So how it work is that first you take this part of that. So for every single point, you grab 4 of those, and then you want to add the top left with the bottom right, and then minus the top right and the bottom left. And if that's positive, then it's a 1. If it's negative, then it's a 0. So that's basically how they get this QR code, basically. So if you look at any single point here, so this point at the right is larger than the left, and these are 0, 0. So 0 plus something larger minus 0 minus something smaller. So it's a positive number. That's why you see a positive point over there. So essentially, you basically just compute the things over the whole things, and you will see that it's like a very unique pattern. It's not like just getting the contour, but also it's sort of like getting a rough shape of your activation, but at the same time, it encodes some of the edge, but also the sharp edges around your signals. So anyway, they figured out that using this is very, very efficient, and you can see all different kinds of fingerprints that you can get from all these things. So it's a little bit tricky to see what's going on, why we are using this filter. But anyway, what they figured out is that this is super efficient and very robust in all different kinds of processing. So, take this audio and then you compute this fingerprint using this idea that you basically just grab the spectrogram and do the frequency banding, and then you apply this convolutional kernel and you binarize it, then you get the fingerprint. So say this is one of the fingerprint that you get. Notice that this is 90-degree, turn 90-degree clockwise, where you have frequency band here. So band 0 to band 31 and time from 0 to 256. So now it's like turning vertically. Now, what if we take this and then, this is a waveform. And then we take a waveform and then encode it with MP3, and then we turn it back. And so, if this fingerprinting algorithm is really good, then, we should be able to still get the same fingerprints. So this is what we get with MP3 at 128 kbps. So you can see that most of the time they are pretty much identical. And if you look at the bit errors, there's much sparser than it's sparse basically. So that's basically the idea of this energy difference space fingerprinting. It should be robust to all different kinds of processing. But at the end, what you get is something that's robust to different processing so that you can do this fingerprinting efficiently. Any questions on this? I have a better slide to show how it works later when we talk about the other algorithm. So, this is sort of the idea. You have an audio, you get the fingerprint, and you have the other audios, you have the fingerprint, and you try to match them. And here, how you match them is basically computing how close their fingerprint is. So you can compute, bit errors. Whenever they don't match, then you have a 1, and you basically sum it up to see how many bits are different. So the other ones, I guess this is more famous because this is the one that Shazam initially started with. So this is like a peak-based audio fingerprinting algorithm. So how it works is basically, looking at spectrograms, it can be noisy because, when you play this song, using MP3, using different algorithm, and, potentially you use your phone to record it. So it could be very noisy. But one thing, unique about, all these spectrogram is that their peak should be roughly the same, right? Even you play it in a very noisy environment, you still hear those pitch. Those are, the dominant pitches. So the idea here is that, these peaks should be very robust to whatever noise level, because these are the most highest activations in your spectrograms. So the idea of this peak-based audio fingerprinting is that, well, can we just build something on top of these peaks? So, you get a spectrogram, you pick the top sort of like 100 of those peaks, and then now you want to try to match this. So how does it work? So in principle, what we want to do is that, well, we won't get, the full sounds all the time, right? Shazam is like, well, what's this song is about? And you record like 5 seconds, 10 seconds, or sometimes even just 1 second. So you will have a query. So you run this peak extraction model or, algorithm. It could just peak, 10, 20, 50 of those peaks. And now, in your data, there will be tons of reference audio. There can be thousands of that, millions or, billions of these songs. But take one of these songs, we know that this is a match. Then how you do it is that, well, first you try, in the first chunk of that, and you see whether there's any match. So in this case, well, there's no match. And then you just keep moving on, moving on, moving on until, at some point, if there's a match, you will see that perfectly lines up in this case. So that's essentially how this peak-based audio fingerprinting is doing. So what you are seeing here is that how you move that query around the reference file. And so, when we started with 0, there could be one single match, but at some point, if there's truly a match, then you will see a huge spike of matching number of matching peaks. And so, of course, out of your catalog, there should be just only one match most of the time, unless there's some sampling, but there should be very few matches. So everything else you will see is something like this. Like, you still sometimes from time to time, you get some of, these are close, you see potentially these two is a match, but it doesn't make much sense because it's just randomly overlap. Cool. So that's the idea, high level idea. But most of the biggest part of this, the biggest challenge here is that how do you do this more efficiently, right? Because you have this query, basically you have all these points, and you want to check whether these points match with these points. How do you even do that? Think about the complexity is huge. It's like for each point, you want to check whether all these blue dots is close to that red dots. So this is potentially an, O n times m complexity because, you have like n points here. And for each slice, you could have like n possible case. So you want to do O n m. So that's, too much of computation. Think about you want to apply this to billions of songs in your catalog. So essentially what's going on is that I won't go into detail, but this is what hashing can be helpful. So the idea is that we want to use some hashing algorithms to reduce that, linear or square complexity into O1 so that we are hashing all the pairs, possible pairs. So the idea is that, well, we don't want to encode all the possible comparison between different matches. We only want to compare those closest possible links. So we are not comparing this point to this point, but rather we pick an anchor point and we encode the distance between these things and these things, and that distance. So the idea is that we want to bring this combinatorial m by m computation down to a linear constant operation. It's a bit tricky to get into details, but you see that audio fingerprinting has two-stage process. First is you get a very efficient representation. And second is that representation has to be hashable or, indexable so that it can run very, very efficient, so that you can run it in billions of matching. So, the idea is that we want to see if there's a match, but at the same time, we want to do it as fast as possible. And that's what this complexity lies in, all about the hashing. Questions on these?
This one question that I ran into a bit was like, when you do the constellation map, do you want to just like do it over the entire segment, or do you want to like kind of window it to like evenly distribute the peaks?
Oh, you mean the peaks? That's a good question. I think you want to evenly do it because when you try to do this matching, you don't want it to be, because if you have the query, you are getting the query to your reference. So you still want that peak to be relative rather than absolute. Yeah, because I think one of the trick here is that audio fingerprinting, when you are slicing through it, you are sort of like doing some sliding window matching thing, rather than you sort of want to have these peaks roughly distributed evenly as what you will have in your grid. Of course, that depends on how you normalize the audio, but basically you want to normalize per slice, kind of. Yeah.
It's I think one thing I think it's just like
Does it work?
there was some
Okay, cool. Then it's good.
maybe certain parts lots of like
Yeah,
concepts going on, and other parts maybe not. Like if you were to do it just doing constellation mapping over the entire thing without thinking about windows, then you have most of the peaks concentrated in like the high volume portion of the audio.
Yeah,
Like
yeah,
any
yeah,
power
yeah.
functions. So like kind of evenly windowing, extracting some number of peaks from each of them.
I could see, yeah, I could see benefit of both. Is that, if you do the whole song and you get the constellation map, then it sort of like capture the peak activation of the whole song. So it makes more sense. Those are the most iconic representative parts of the song. But at the same time, it's like, well, we just want the intro that's like soft piano. And if you want to do a match on that soft piano intro, well, that might be something people want, but at the same time, it's not the most iconic part of that song, potentially. So I guess this is about numerization. But one thing about P-based audio fingerprinting is that it does also doesn't really depends on numerization because you are doing max, so you don't really care about how many noise you have and what's the range of that, because you basically just pick the top 10 peaks kind of. So this is one of the benefit of these peak based audio fingerprinting. And one thing you will also see, this is the same feature of energy difference based algorithm, is that all these fingerprinting model try to avoid something, is that we don't want to have an absolute value, because sometimes you record it through phone, sometimes you use a different codec. So oftentimes you want to compare to yourself. And what this thing is doing is that whether in the next frame we have a larger energy, and in the same frame at the higher frequency band is like a higher activation at that point, and look at the next frame and next frequency band. So what's the difference between them? So, it's called energy difference space because we are technically finding the difference across temporal and frequency at the same time. So, um, these things minus these things is basically on this frequency range. What would be the next frame and this frame? Is the next frame louder than this frame, right? In this frequency range. And then look at this. If you think about it as minus plus minus. So it's like the next frequency band is the next one louder than this one. But now you want to see these two difference. So it's a little bit tricky, but this is basically the difference of difference, the difference over frequency of the difference over tempo, the energy. So you are doing double, sort of like double differential computing here. And that's why you get all these very chaotic kind of QR code, or the bitmap in the end. But at the same time, these are more robust to the absolute value, because we don't want absolute value in most cases for fingerprinting, because we don't know what the level of your audio is. You just want to know, well, is like more like a C rather than C sharp kind of thing. So that's the relative part of it. And that's applied to peak bass because, basically this to this is getting rid of all the noise. You only look at the most highly activated parts of that. Cool. Anyway, we won't go into details, but, part of the technical challenges in, how do you turn this algorithm much faster, in a sense. So this is actually being used, if you're a video editors, then you likely know the YouTube's, very strong content ID. But basically, YouTube nowadays, some people just joke like, if you want the best, audio fingerprinting algorithm, just upload your audio to YouTube and it will do it for you. So that's how powerful YouTube's content ID is for. But at the same time, if you're a video creator, of course, you might find it very tricky to work with this, very strong content ID algorithm. But at the same time, think about if you are an artist, like someone might just accidentally, or not accidentally, intentionally infringe your copyright. So these content ID is a very powerful way to sort of like mark that, so that that potentially they should license it, or potentially you should block their usage of your music or your content. So this applies to mostly audio in this case, but this is based on these fingerprinting algorithm to do that. Um, So yeah, I mean, from time to time, even if you're recording something and on the road and someone just passed by playing some music, you will also trigger it. And there is also the case where I think in LA, like when LAPD approach you, they will play sort of like Taylor Swift songs so that it will be marked by YouTube, Scandinavia, or Disney songs, so that it will take down the video for you if you don't want to be recorded. So this is how powerful these models are. Anyway, if you're interested, there's like a kind of old review paper on this, 2005, 2005, but these algorithms, one is like 2003, the other is 2005, 2002. So, this is a very old techniques. But nowadays, people are also looking into can we use deep learning to get those representation. But at the same time, again, fingerprinting is two parts. One is getting the fingerprint. The second part is how do you do the matching as efficient as possible. And for that, it's very technical, and oftentimes you have to have the um, outputs hashable, which is something we won't talk about. But is something hashable or not? That's a big question in database system. Cool. So something sort of like keep going on in fingerprinting is that now you think about different versions of a song. Think about cover song, think about someone just whistling the same song, or someone do resampling, someone do arrangement. So this is actually a much broader case where things become a bit more trickier and trickier if you think about how far away you are from. So this is like a paper recently on audio-based musical version identification. So, at the very left, this is like duplicate. So, of course, duplicate meaning that nothing can be changed. But, think about remaster. So, nowadays you will have the song remaster, using the same, tape, and you want to remaster it, then potentially you introduce different noise to that because of your equipment, how you master it. And then, radio edit, translation, performance. So performance, you might change the tempo, timing. If you're doing demo, then potentially you will do everything differently. But also, a bunch of things. And all the way until, you have remix, you will have cross-genre arrangement and quotation. So at the very right is, things that become more drastically altered, where your music will be changed, kind of. So, version identification is beyond fingerprinting and covers, but all the way toward, maybe you are just referencing an audio, a music idea that you are very interested in, and how do you even detect them? Of course, cover song identification is one of the things. So, the way how you can do it, this is like one example model that you can do cover song detection. But, think about you have like an audio to audio, and what you want to do is to do singing voice recognition because, in cover song, meaning that, well, potentially your singing voice should be the same. And so if you can do transcript to get the lyrics, it will be much more robust than just looking into the arrangement because the arrangement could be different. So whenever you are thinking about this version identification is that try to disentangle your inputs audio into multiple aspects. Lyrics, vocal, genre, or, timbre, or, the vocal characteristic, and arrangement about, chords, keys, those very high level chord progressions, higher level music features that will help you to do better this version identification. So taking it even further away is like something that we been using for years. So this is how to search, but in the past more known for query by humming. But basically, Google sort of tried to reinvent the wheel. But anyway, now Google has this hum to search feature. I tried to search whether Siri had this, but I couldn't find it. But I doubt. I think they also have the same things. But the idea is that, well, can we sort of like, do you know what that song is? That's Bella Ciao. Do you know Bella Ciao? Have you watched the Netflix? The Money Heist. Um, but anyway, so this is sort of like hum to search. You can hum, or you could just you whistling. So that's sort of the idea. And if you look at the actual recording, that's just this is like a A/B test of what your humming is like, and this is the studio recording. So even from the spectrogram, you can see that if you want to do fingerprinting, this won't help at all, because you don't have all the instruments. Here you see all the instruments, and you see the vocal, but at the same time the vocal is highly fluctuated, in a sense, and it could be potentially also different keys, right? So we don't exactly know what's going on, but these are some of the things that they show. But basically, you have the humming audio, you have the recorded audio. If you can train these kind of models so that you will get embedded and you can try to do it. But the idea is that how do you even get better? How do you get these kind of audio to train it? So one thing you might think about is that traditional way of doing this is just do pitch estimation. So once you get the pitch curve, like the two things, the relative pitch contour should be the same. So you could potentially grab this and you do pitch estimation, and you grab this and do pitch estimation. And the goal is try to see, can you shift that pitch contour so that there's a perfect match. So this is kind of the traditional approach, but you can also do it with deep learning. But the idea would be, how do you do it efficiently? How do you get these kind of data? So there's no way we would just randomly record like huge data set for hum to search. So in this case, they are thinking about, can we use data augmentation to do it? So, this sort of like approach deep learning research in a different way, rather than collecting very tricky to get data sets. But now can we think about, can we generate some data to train these kind of data? So this is what I did. So
Freude schöner Götter, Funken, Tochter aus Elysium.
So the idea is that, well, we do have a bunch of, these kind of like singing voice data set. We don't really have these humming data set because, it doesn't make much sense. I mean, in this case, makes sense, but, in general, it doesn't make much sense if you or randomly have a huge data set of, oh, the humming voice. But one thing we can do is that, well, we can actually get the pitch from those, and then we can just apply a humming sounds to that. Cool. And so this is another version. Whistling. So this is essentially how they get a bunch of, pair hum audio and the aligned recorded audio. So you have a song, so you have the recorded audio, and then you grab the singing version of that. But now you turn that singing version of that into a hummed or, whistle audio. And now you get this pair of audio. Now you can train your deep fingerprinting algorithm. And of course, you can also do it in a traditional way where you are grabbing the pitch as pitch value and try to do matching to see whether there's an alignment. But in this deep learning era, one thing nice about deep learning is that you could potentially get an even more compact representation to describe your audio that capture those very unique representative features for you. Cool. So again, we will go into much detail of this, but there's also very nice tutorials on this version identification in the 20s. So version identification is still an ongoing task. So think about cover song detection, and nowadays in AI generated contents, this era of generative AI. There's much more challenge in version identification. Say, you grab an audio and then so have a music and go through VanNet that we talk about, right? VanNet can sort of like recreate your music, but don't move so far away from that. how robust is your version identification, but at the same time, legally or, I don't know, technically or theoretically, how far away you are recreating the song from, you are doing adaptation to your original songs. So that's something, the boundary keep moving. And nowadays, with Gen AI, this boundaries become even trickier to maintain. And that sort of bring us to this music watermarking things. So this is sort of like, in the past is like, well, can we sort of like add a trademark or music watermarking onto our audio so that, when people share around the music, you do know that's, licensed and you don't have the right to share that. So this is like audio watermarking. So the idea is that can we add a very tiny watermarks in your audio. So think about, you are hiding some message within your original message. So, back in World War II, World War One, all the audio telegraph, people might want to install some of the code within that message. So the same idea is that can we hide some information within the audio so that it sounds the same, just that there are some additional information of that over there. So, the idea is that we have like a watermark generator that install some, or hide some information in your audio outputs that it's not audible or, very tricky to detect. It won't change the sound, but at the same time, you will be able to detect whether there's something over there. And your goal is to see if you can do no perceivable difference. So there's a bunch of usage about, these audio watermarking things, but I guess, now in the Gen AI era, one thing that's very useful is that can we do audio watermarking against generated audio? So this is actually being done in some of these Gen AI company because for legal, but also business purpose to see whether they can install these watermarking into content generated by their system so that they can detect it. So this is actually implemented in a lot of like speech generator, but also, Google's Music FX. Now, when you generate some music from their platform, they will hide some of the watermarking in their outputs. And hopefully this will help, these companies to detect whether something is generated by AI. So that's the idea. So, what you want to do is that, well, you have some speech model and you will generate some, some speech, right? And the goal is that for these company, they want to generate some watermark on top of that AI generated song. So think about, 11 Labs, like one of the iconic, speech generator startup, then potentially they generate some speech outputs and they want to speech audio, and then they want to add watermark on top of it. So the idea is that potentially the negative or the bad way to use these kind of model is that potentially you will edit part of the video or the audio content with LM or Gen AI generated speech. So the idea is that can we sort of like detect this? So the goal is that once you have this watermark speech output, and when you install or put it trim or rearrange and put it into a larger audio chunk, and can we have this kind of watermark detector to see that, well, other parts is not generated by AI and we want to mark those parts that's generated by AI. So this is essentially what this work is doing. So this is called audio seal. So what it does is that, well, we will have the original audio and we want to generate some watermark generator. And how it works is that now you want to train this model by augmenting the original audio and you mix it with the new watermark model. And how you want to train it is that this detector will be trained to, predict whether there is a watermark outputs there. So the goal is different for the generator and the detector. So the generator is trying to minimize this perceptual loss. But at the same time, the detector should be as high as possible on that base. So this might remind you a little bit about the GN things, right? The generator and the discriminator has sort of like a, like a different goals. So in GN is like generator trying to generate something real as possible, and discriminator try to distinguish from real from fake. And here is like, well, you have this generator that trying to do as little as possible. I don't want to change my inputs drastically. I just want to instill tiny information in that. And at the same time, this watermark detector will be trying to encourage that, you still want to do very good at, having this detector to detect your outputs. So potentially, you have to hide more information so that you can do a better job detecting the watermark. So this is like a conflicting trade-off between these two goals. One is that, well, I want to install some information that I can grab at second stage, but at the same time, I don't want it to be perceptually audible. So we can listen to some of the examples here. So here this is like magnified by 5 times. So, these are actually much smaller in its energy. So the outputs will be detected. So, this is the original audio and we added these things. This is like 5 times larger than the energy. This is what we hide in this audio. And you will see that, the detection will be almost 0 and jump to 1 here and then back to 0. So the original sounds like this. Likely, we won't even hear the difference here. And this is the watermark version. I think there's definitely something going on, but just not so obvious. And this is so most of the case, you wouldn't tell the difference. So that's the goal of watermark, right? It's like watermark shouldn't affect your understanding of this music or the audio. And it will be unnoticeable unless you run your watermark detector so that you can see where are those. So this is actually an ongoing efforts in the field where, there's also this audio mark bench where you have different data sets and different watermarking methods. There are several of those, and, there are tons of different kinds of attacks. So there will be no box perturbation, you will time stretch, you add some background noise, you want to do MP3 compression. So the goal of these watermarking algorithms is that you don't want it to be easily bypassed by some of these easy hack, right? And also there is also black box perturbation, meaning that I don't know exactly what watermarking methods you're using, but there's a white box perturbation if they know what your model is. And the goal is to see, can we prevent people to remove that watermark or, to bypass that watermark detector. So, these got all sort of different kinds of attacks that you want to prevent from. So this is actually being adopted in MuseFX and some of the other speech, generation model. So, in MuseFX, you will see that, use Google Demise novel watermarking technology, since ID to enable a digital watermark in the output so that, Google can detect whether these are songs generated by MuseFX. So this is like music watermarking. So, we go through some of the things, fingerprinting. This is about search, watermarking, and also, version identification. But this is sort of like, think about more broadly, there are so many different applications. One is like identify which song you're listening to, but at the same time, in this era of music, Gen AI era, then we do want to know whether this song is, infringe the copyright holder, but at the same time, are these AI generated? Question on those? Cool. I guess these are more business to business idea. For user, likely is less of interest that you might notice that's even running those. But if you are an artist, then definitely you want to protect your copyright. Cool. So the last thing we want to talk about is music recommendation. So this is the last technical module. There's still several slides. But music recommendation is one of the things that you might be most familiar with if you engage in music listening. So these are actually ranked by the popularity in the States. So Spotify, Amazon Music. I was surprised how big Amazon Music is take the share. But these are paid users. These are not just free tier users. So if it's free tier, I bet the ranking is a little bit different. But anyway, Spotify, Amazon Music, Apple Music, YouTube Music, and Pandora. So music recommendation. The simplest question is, what to play next, basically. So you have a huge catalogs here. I'm using the album art to visualize this for easier understanding. Otherwise, there's tons of songs here. There's no visualization of those songs. But anyway, you sort of get a sense, potentially I'm referring to one of the songs, but there are billions of songs in your catalog. And, music recommendation is to leverage any information about, the contents that you have these songs. What do you know about these songs? Do you have the metadata? Do you want to use automatic music analysis tools to understand these contents? But at the same time, how does what other user interact with this catalog? Can you learn something from that to do a better job on music recommendation? So one of the iconic way of music recommendation system, rather than just music recommendation, is called collaborative filtering. But the idea is kind of simple. We can just go with it. So think about that, for example, if we have like 6 albums or 6 songs or 6 artists, in whatever way, like 6 different items, and you have the first listeners that listen to these 4 songs. And then you have the second, the third, the fourth, and the fifth listening to different songs, right? So, once you have this kind of like table where you have the item and user interaction table, so a check mark, meaning that there's some interaction between that. So now you can see some pattern over this that, user-based collaborative filtering is that, well, these 2 users seems to be similar to one another, right? Because they have the same sort of taste of music. And so this is like collaborative filtering is about. Now, what if the user listen to a new song? This is like Polyphia. I forgot their band name. That's very nice if you want to listen to some of the cool music, new music. This is one of the band I really like. So, if you listen to this new album that just released, then potentially, because these 2 users have similar tastes, then you can potentially just recommend that music to the other user. So this is sort of like the first thing we can do about collaborative filtering is that using the existing understanding of your music database to see what are the similar users. And then, if this user listen to a new music, then potentially we can recommend the same music to the other user that has the similar taste. So this is called, user-based collaborative filtering. But at the same time, now we can look into item-based collaborative filtering. So now, let's look at these 2. These are classical music and, film scoring. This is also a very nice album, John Williams with Motor on Across in the Stars, so Star Wars suite. But anyway, you will see that they have been listened by the same sort of groups of listeners. So you sort of knows that these are similar items or similar songs, similar albums, similar artists, or similar genres. And now what you can do is that, what if this listener listen to this album, then you sort of know that you can potentially just recommend this user to listen to the other similar item. So, that's basically what this item-based collaborative filtering is about. So one is about, looking at what are similar users, and then you can recommend the same songs listened by user A to user B. And now here's item-based collaborative filtering, looking at how similar these items are. Then once the user listens to one of the item, then you can recommend a similar item to the same user. So this is just a way to look at for this collaborative filtering. So what are the challenges? You might be wondering. There's actually tons of challenges here. First, it's like, well, most people listen to sort of the same songs. Mostly, if you go to Spotify, Billboard 100, then people tend to start with those, and then other less known artists get the fewest listens. And that's one thing. And the second thing is like, what if you don't have any things, you are building a new product, you are, a user just recently signed up with your platform. There's no way you know anything about what this user like. So there's tons of challenges here. Like here is like assuming you have a good enough system that you have tons of, catalog and you have all the users. And at some point, people will listen to different songs so that you collect a bunch of data. Then you can fill in the blank. But what if you don't have those? So there are like tons of challenges in music recommendation, but also, in general, recommendation system. So think about Amazon, video, film, like Prime Video, like how do you recommend video? Netflix, what should you look at next? And, they want to do profiling. And so this is actually a huge business behind recommendation, because nowadays, you don't have much time to look at all these content, even, all the different platforms, or even gaming is like, what should you try next with this? What are the new games that you recommend to you? Or think about Amazon shopping, fashion, online shopping, all sort of things. So this like long tail problem has been known for a long history of time. So at the x-axis, this is what we call long tail. So at the axis, you can see this is the rank. So this is the most played song, second most played songs, third most played songs. All the way here is like the tens most played song. This is the hundredth most played song, and this is the thousand most played songs. So this is like a sort of like a million database. This is like being done in 2010. So this is like their data set is like a million songs, and they do have all the listening behaviors. How many listens do you have for each songs? And you can see that for these 0.1% of songs that actually have much higher listens than all the songs after that. So this is what we call long tail, meaning that everything here is not so commonly listened to by your users as a whole. So there's actually a famous observation or a famous joke in recommendation system, like for film recommendation system, is that whenever you train a video recommendation system, is that just recommend Harry Potter 1 to 7, and you always get the best, performance on all the metrics. But it doesn't make much sense. It's like, is that what we are aiming for, recommendations? So there's tons of, aspects that we need to take into account of recommendations. Sometimes you want it to feel like, well, this platform is trying to extend, is exploring, discover some of the new things that you don't know, but at the same time, it wants to keep you engaged rather than, proposing something too drastically different from your own taste. So it's always drawing a balance between, exploration, but also keeping your comfort zone. So these different platforms sort of have different behaviors. So there's also that's not called star problem, called start problem. So what if we have a new items where, you have no ideas what the, user interaction with that new album will be. So fortunately for new items, we do have some ways to do it, and so this could be relevant to some of the music analysis things we talk about. So genre identification, or just looking at the metadata. So this is called content-based filtering, where we do know something about these new albums, right? We do know that they are both musicals, they're both live concert version, they are both, concert at Royal Albert Hall. So potentially once a new album release, you do know how it connects to your existing catalog. So in that sense, you don't really need to just look at, previously in this item-based collaborative filtering. You don't necessarily need to look at the user item interaction to see they are similar. You could do it through looking into the content itself. You could potentially do, your metadata, or, you can do all sort of like music analysis, things that we talk about, key detection, artist detection, instrument detection, genre classification to see what these content is. And so that you can do this content to content model. So the difference between collaborative filtering versus, content-based filtering is that collaborative filtering is talking about the similarity between the interaction. So the core idea is that, these two users listen to the same albums. These albums are being listened to by both users. So they are similar users. So now once what user A listen to a new album, then you can recommend that album to user B. So the way how we model whether these users are similar is through their behaviors interacting with the catalog. But content-based filtering is different. Is that we just look into these two albums. We want to see whether they're genre match, whether they're, I don't know, instruments, or I don't know, musical, or even the venue. How can we look into the content and make sure they are similar items? And once you can do that, then if this user listen to this album, then you can potentially just recommend a similar item to them. So that's one way we could potentially alleviate this code start problem. But what if we have a new user? Then that's another even more tricky things. I sort of stuck with YouTube Music. I tried Spotify once, and I tried Amazon once. And then nowadays you will see that they used to have some like sort of like pack your data up and then trying to go through another platform. But nowadays, I think they are closing that. So nowadays, each of these platforms sort of understand what you're doing, and it's sort of like your autocomplete will learn over the time, so that it knows your writing styles. So that's sort of the same idea. Once a new user sign up in the platform, you don't really know what they like. And oftentimes when you sign up, it will ask you like, who are your favorite artists? What are your favorite songs? Then that's provide a good start. But anyway, there's also some other things that you can do. This is like good old techniques, user profile modeling. You could definitely look into some of the things. Nowadays is a bit really tricky. Geographic, you can easily get it, but demographic, likely no one will ask these nowadays. But it used to be a thing, but nowadays, more privacy concerns, so can be tricky to get these demographic information. But this is generally we want to model a user. And this is also something very interesting that I found out while researching about this topic. So this is like a study by UK, I believe. So 27. But basically, this is our distribution of people interacting with music. So surprisingly, only 7% of the general public, everything in life seems to be tied up with music. And there are like 21% music is a key part of life, but it is also balanced with other interests. And then it's like music plays as a welcome role, but other things are far more important. And sadly, the last one is the biggest chunk, 40% of people is like will not lose much sleep if music ceases to exist, which is sad as we are talking about this class on AI and music. But at the same time, well, this is a real life demographics of the public. But you know, the good thing is that 60% of people are interacting with music anyway. And sometimes, you know, music is so pervasive. So, you know, it's like they will still live well with some music, but at the same time, you know, music also part of our life. It's kind of hard to get rid of it, kind of. But you know, one thing we didn't also talk about, I mean, I talk about it a little bit about it, is like this trade-off between music recommendation system is that, you know, usually we look at, you know, this is like a nice figure showing that. So at the x-axis is the relevance. So when you want to recommend a new song, or you know, recommend what to play next, or generate a playlist, you think about how relevant it is to your original taste. So you know, you've listened to thousands of songs, what should be the next song to recommend? Should you just do the same songs, or you know, you want to bring in a new songs? So that relevance, if you just recommend something that's, you know, very the same as what you listen to, or you want to get something different. And novelty is another thing to look into. You want it to be something drastically different from your catalog. You have explore, or you know, something that's within your space. So this bring us to, you know, different case. You know, we will have, you know, if you just do, you know, all the time Billboard 100, then you will have somewhere here that's just recommending all the popular items, popular songs. And, you know, that could work as a start. But, you know, this like random part is where, you know, you think about, well, I just generally just random pick a song. It's not relevant to your own, you know, listening history, but at the same time, you know, it's so novel, which is nice, but at the same time, it's too random. So these two things are likely not something we want. We want something in this space where, you know, explore is sort of like getting a nice trade-off between, you know, we want to explore a little bit, but coming back to your songs that you know, and then you explore a little bit and coming back. But oftentimes you can also have like discovery mode where you drastically going around your space and try to find something that's, you know, relevant to your songs, but it's totally new that you haven't listened to. And this like laid back thing is basically, well, I just keep listening to the same songs, but those are songs that I've listened to. Rather than, you know, like the popular case is that these are songs not personalized to yourself. These are just songs listened by other users. So, you know, in this space, there are different modes that you can move around, and, you know, people have different behavior. So one thing very interesting about, you know, YouTube Music Recap is that it will sort of like show you your listening behavior. And this is Spotify's, you know, listening personality, which I think is very interesting, because I feel like I am more like the replayer kind of folk. But over the time, there are also people like to adventure around their music space. So, you know, I guess in the future, what we will see is these music recommendation system will become more nuanced with like personalized to your own behavior, so that if you want to explore, or even you can have a switch that this is discovery mode. This is, you know, nowadays you have like discovery mix, explore mix, or, you know, just replay, you know, favorite songs basically. And there's also the idea of like, it's not just about the next song only. You potentially want to create a playlist. But at the same time, it's like, you know, the biggest challenge of these music platforms is so that you stick on that music platform as long as possible. So even when you are doing this music playlist generation, you shouldn't assume, you know, people will listen it through all of it. So, you know, the earlier in that playlist is more important that, you know, later songs in that. And also shuffling, does shuffling affect the listening behavior, or you have album. Usually in the past, people think too much about how you should order the album, because you cannot easily shuffle around different songs. But nowadays, streaming just keep changing that definition. And nowadays, I think there's recent study about whether shuffling changed the listening behaviors. And I believe what they're finding is that shuffling doesn't really change a lot of the playlist behavior. So sequentially or shuffling, or how does music playlist go beyond just one single next song prediction? That's interesting ideas. And still lots of research going on for that. I think I've talked about this once, but YouTube Music now has this S Music, basically LM. You can chat with it to generate new playlists, Spotify AI playlists. But I think this is the latest one, personalized picks in ChatGPT. So now you can, in ChatGPT, you can say something like generate a Spotify playlist, something, and then you can open the Spotify. So this is one of the iconic partnership with ChatGPT to sell their API basically to companies, so that these companies can have a sort of like a plugin into ChatGPT, so that ChatGPT access a portal where you can sort of like do search or do commands like a vocal assistant basically, and it will launch in the app that you are using. Well, there's tons of challenges still in music recommendation, but in general, recommendation system is a huge field where tons of ideas floating around, tons of research going on. But if you're interested, there's a tutorial. There's also a nice review paper here. Cool. Any questions on recommendations? Kind of roughing through it.
I guess if the thinking about songs being in a playlist, combines both of the sides that collaborative based into, where a user put a song in a playlist, that's especially a good indicator that they like it, and also songs in the playlist are similar.
Yeah, yeah. Yeah, I believe some of these companies might using these. So I guess that's also another tricky thing about doing research in this field, is this is so commercialized. And nowadays, in the past, there are also, like online forum or platform where people are sharing these, user interaction data. But nowadays, it's very tricky to get these kind of interaction data, because that's essentially how, they can compete with another yeah, there's still some data set, last.fm. This is I think the last.fm. So the long tail, there are some data sets. So this is definitely from some data set, right? So but the same as Amazon data set for online shopping behavior or recommendation. There are some Amazon review data set, Amazon interaction data set, but it's never gonna be the huge data set of what they are using internally. Yeah, highly commercialized, but at the same time, understanding how it works also help you sort of, I don't know, does it help? Like when you're listening to music, you're sort of less controlled by these models, but you sort of know what's going on under the hood. Cool. Cool. To recap, now we are in the streaming era, kind of. And we talk about your fingerprinting, basically grabbing these fingerprints. And the goal is one, compact, efficient fingerprint, very accurate in matching. But at the same time, we want to have this matching to be as efficient as possible. So we talk about two kinds of models, but here peak-based auto fingerprinting. This is the one used by Shazam. So the iconic one, but basically, just looking at the peaks. So these will be more noise robust. So we get this constellation map, and the goal is just to try to slice this query through your reference and see whether there's a match. And so hopefully we find a match, but the idea will be how do you compute this efficiently? And that requires a lot of hashing algorithm designs. That's the technical components of that. But the idea is that we do want to do this matching, and we want to do it as fast as possible. And that's go beyond just, the same duplicates. So, fingerprinting sort of like duplicate or remaster or, re-record sounds. But, going beyond that, there will be demo version of that, cover version of that, karaoke version, live version of that, or, a remix, cross-genre rearrangement. And finally, it's just a quote. Then it will become much trickier than, just fingerprinting. So we have to think about other ways to do it. So one of the iconic application is hum to search, where you just hum or whistle, and can you do pitch recognition or, to do something so that you can do this efficiently. And we talk a little bit about your watermarking. Of course, it's sort of like a detour around our topics. But this has become a huge thing nowadays because of Gen AI, that basically you want to instill or hide some information within your audio that is like detectable by your own watermark detector, but at the same time, you don't want it to be perceivable. So this is nowadays, generated audio. People always wanted to, have a watermark on top of it so that you can prevent these, unwanted infringement or unwanted, ways of using these kind of models. So this is the audio seal. You can basically hide this message inside your original audio, and it will be, perceptually indistinguishable from the original audio, but at the same time, your detector will be able to detect those. And lastly, we talk about recommendation system. So, we talk about collaborative filtering, basically looking at this user item interaction map. You can sort of like understand a lot of, users, similarity, but also item similarity. So if you do know they listen to the same set of, albums, you sort of know they are similar users. So then you can do this, recommendation to the users. But at the same time, if you do know they are similar albums listened by a similar group of users, then you do know they are similar items so that you can recommend the other song to the same user. But there's tons of challenge, this long tail issue where, most songs don't really get a lot of listens. And most of those focus on the not long tail, the first 0.01% of songs. And there is also cold start problem where you have new items, then you don't really know what's the potential interaction. But hopefully, or fortunately, we likely will have some metadata so that you do know these albums is similar, so that you can do recommendation on that. And what if you have a new users, then you can use, listening experience modeling, user profile modeling to sort of model the user that you have. And of course, this is a huge space where you basically want to balance between the trade-off of like exploring something totally entirely new, but at the same time, you don't want it to be too boring, just listening to the same songs again and again. Cool. I guess that sort of summarize or finalize all the things we want to talk about in technical content. Next Monday, we will look into some discussion and, sort of reflect what we are doing in this course and what are some of the concerns and challenges of music and AI. And of course, in the field, there's tons of discussion that we didn't really touch on.